Okay, we obtain another integral. We've got the integral from 0 to infinity of 1 over x to the 2024 plus 1 dx. Okay, right away, the disturbing part in this one is just this exponent here. If this was a lower power, what we could do is probably partial fractions, try to do some kind of factoring on this, do the normal ways. With 2024, I don't think I want to try partial fractions. So instead of that, what I'm going to do to try to transform this is go directly to a u substitution for basically the whole thing, just kind of create a 1 there. And I want my u to be x to the 2024 plus 1. We could take a derivative here, but I think what I want to do is solve for x first. It's going to be about the same. Either way, we're going to have some mess to deal with. So solving for x, we'll just kind of cross multiply. We'll have x 2024 plus 1 equals 1 over u. But then let's subtract 1 on both sides here like that. And then next, I think let's get a common denominator on this. I can write 1 as u over u. So what we end up with here is 1 minus u over u is going to be equal to x to the 2024. But in order to isolate x, let's just take the 2024th root on both sides. So this ends up being our value for x is going to be 1 minus u over u to the 1 over 2024. So now let's get rid of this mess and let's just take the derivative now that we've got our x isolated. So when I do that, what's going to happen is we end up with, we have dx is going to be, first we need power rule. So then we'll have 1 over 2024 in front, 1 minus u over u, minus 2023 over 2024. And then on this part, we need quotient rule. Let's see if I have enough space to squeeze it in over here. So first derivative of the numerator is just going to be a minus 1 times the denominator, which is just a u, minus, we're going to bring back the whole numerator, 1 minus u. Derivative of u here is just 1, and it's going to be all over the denominator squared. But then when you clean up this whole numerator, the u's are going to cancel out, and this whole thing becomes a minus 1. So all I'm going to do is take this minus 1, let's just bring it over here, and simplify this whole numerator down to just 1. And now we've got a value for u, x, and dx. Let's go ahead and substitute. So first, let's plug in infinity in here. When you do that, the denominator blows up, so we get 0 for the upper bound. And then you plug a 0 in here, you just end up with 1 over 1. Lower bound becomes 1. Now for the whole integral, again, we just called that u, so we're just going to have a u right here. And then for our dx value, we have all this. So let me just copy all this stuff in here. And now at this point, this looks like kind of a mess, but we've got a lot of simplification that we can do. First of all, I could take the minus sign and use to flip the bounds, so we can get this going from 0 to 1. I can cancel this u with one of these here. This part's a constant that we can bring up front of the integral, so when we rewrite, let's see how it goes. We're going to have 1 over 2024 in front. Now we're integrating 0 to 1. And then what I want to do is let's separate the u terms from the 1 minus u terms just to try to get this cleaned up. So what we're going to have, if I pull this out with this exponent, because it's in the denominator, it's going to flip the powers. This is going to become u 2023 over 2024. And then we have this u in the denominator, but I can write that as a minus 1, just combining our u terms. And then for this other part, this is just going to become 1 minus u minus 2023 over 2024. One more thing I can do on this to set this up, let's just notice for minus 2023 over 2024, I can write this as 1 over 2024 minus 1. And so then let's write it like this. But what we notice now is this is perfectly set up for the beta function. We've got our bounds, right, going from 0 to 1. For the exponents, it doesn't matter which order we choose these in. You could flip it and it's not going to do anything. So we can call this like our z1 value. And then here, this can be our z2 value. So then we can just go ahead and apply the formula here. We just have to remember that we've got this constant value up front. So we'll bring that over. And then with the formula, it's going to be gamma of the first value times gamma of the second value over the gamma of the sum of these. So we end up with, for our z1, it's going to be this. And then for gamma z2, we're just going to have 1 over 2024. And the nice thing about this, when you add z1 and z2, what you get, it's just 1. Now for an integer value, we have this formula. We can relate it to the factorial. If you have gamma n plus 1, this is going to be the same thing as n factorial. So in this case right here, using this is going to be 0 factorial, which just equals 1. So what we can do is just get rid of this. Don't worry about that. And actually, we do have kind of a solution right here, but it'd be nice if we could find a way to simplify this or write it in a different form. You may notice this is exactly in our form for Euler's reflection formula. Euler's reflection formula is going to be gamma of 1 minus z times gamma of z. This is going to be the same thing as pi over sine pi of z. So because our z1 and z2 add up to 1, this here is in exactly the right form. We can use this. You can use it either way. You can call your z this one, but I think it's maybe nicer to call this our z value in this. So putting this all together with the constant in the formula for my final solution of this, we just get pi over 2024 sine pi over 2024, and that's it. And then at this point when I was doing this, I was thinking this is actually kind of a lot like a problem I did just a week back or whatever we did the integral of tan to the 2024, so it had that in common. But then it was also the fact that the final solution wasn't that satisfying because it's kind of like, okay, what is this as far as a decimal number? Is there a different way we can express this? Well, one way to do it would be to use a calculator. Another way is the graph. The graph's really interesting because if you look at it, it's just like a square. I mean, it's actually not exactly a square, but it's very close to being a square with sides of 1. But what I wanted to try to do is see if we could estimate this a different way. Let's just take this 2024 and bring it into the numerator. So I could write this as pi over 2024 over sine pi of 2024, pi over 2024. And then just notice this value that we have. First of all, we've got the same value as the input on the sine and in the numerator. And this value is pretty close to 0, right? Like you're talking about basically 3 divided by 2024. So this is getting pretty close to 0. And so this is looking kind of like this very famous limit problem when we have limit as x is going to 0 of just sine x over x. This value is equal to 1. But one thing we can do with this, because the reciprocal of 1 is 1, we can also just flip this and we can say the limit as x is going to 0 of x over sine x. This is also equal to 1. And now just to be really clear about it, like 2024 is not infinity and these are not really the same things. We're just using it as an estimate. We're saying this is a pretty small number. So just using this limit as a pretty good estimate, we can say this thing is approximately 1. And again, like I said before, just looking at the graph, you basically have something really close to a 1 by 1 square, which also has an area of just 1. Okay, so there you have it. Another interesting problem using 2024. Thanks everyone for watching. Have a good day.